Hello and welcome to Fundamentals of Reinforcement Learning, Part 4. In the previous three parts, we discussed basically the very basics and fundamentals of basically most of the terminology related to reinforcement learning. We also discussed an algorithm or smart algorithm for implementing reinforcement learning on MapRover. In this part and in the next two parts, we will be basically discussing temporal difference learning, sometimes called the TD learning. And in this particular part, we will build the mathematical background for temporal difference learning. And in the subsequent parts, we will be actually examining the famous algorithms that fall under temporal difference learning. One is SARSA, which is sometimes called the on-policy learning, and the other is Q learning, which is sometimes called the off-policy temporal difference learning. And in the final part of this video series, we will be actually implementing the Q learning algorithm in Python, in NumPy, basically in Scratch and NumPy, from Scratch and NumPy, on our MapRover example that we have seen in the previous parts of this video series as well. So let's dive in. Before moving towards the temporal difference algorithms, it is good to actually set up some notation of expected returns. A return at a state st, if you're sitting in state st and you pick some action a and you reach to some state t plus 1, and in that course, if you have received a reward, immediate reward as t plus 1, then the return is all the rewards thereafter that you're expecting. For example, this is the immediate reward, then you move to some other state. In that state, you have chosen some action and you have received this particular reward. Then you move to some other state, you have chosen an action, received this particular reward, and so on. In the very linear form, if we write t plus 1 plus all the future rewards, obviously all these rewards, they depend upon the action you have chosen in future. So this is called the return at state t. And if we discount the future rewards, if we give less importance to the rewards that are very far away from the current state, then we can discount each reward with a discount factor, gamma, where gamma is a positive number, maybe 0 if we want to rely particularly on the immediate reward, and that can be less than 1. If it is equal to 1, then that is the plane, kind of the plane function, where all the rewards are have equal importance no matter how far they are in future. If this value is less than 1, then the rewards that are far away in future, they are less important in contributing this return. And further, if the value is close to 1, then the future rewards are more important. If the value is closer to 0, then the immediate reward and the very reward that are very local, they are more important. So, so this gamma is a hyperparameter that we have to learn. So this is the notion of reward, the return. This is called the return. Return means the all future rewards that you're expecting. So then, if you do a simple mathematics on it, and if you take a gamma common from here, then you can end up RT plus 1. If the gamma is taken common, then you can get this expression, which basically is GT plus 1. So one can easily write GT, the reward at the return at time t, as the immediate reward plus the discount factor times the return at the next state. And obviously that return carries the information of all the rewards that are coming in future. One thing that we must notice is that this GT, it depends upon the rewards in future, and the rewards that you will receive in future, they are all random. So they are random variables. Why they are random variables? Well, there are basically two kind of processes. One is called the stationary process, in which the reward distribution is fixed over time. The other one is called non-stationary processes, in which the distribution of rewards is not fixed. The distribution itself changes over time, but whether it is stationary or non-stationary, it has a distribution, and so it is random. From a particular distribution, the sampling of reward can be done at random. So that's a random variable with a particular distribution. If the distribution stays fixed over time, that the whole process is called stationary. Otherwise, it is called non-stationary. But either way, it's a random variable. Because the rewards, the future rewards, are random variables, the function of random variables, which is gt, itself is a random variable. So rather than talking about return, we may talk about the expected return, which is the expected value of a random variable gt. And here we basically set the, if you're given a policy, remember the policy is mapping from state to actions. It sometimes gives the probability that maps the state to action. So so for example, given a state, the probability distribution for that state for all the actions, that is basically a policy. And you can change different policies, you can set different policies. The whole goal in reinforcement learning is to learn the optimal or the best policy. But it turns out that learning the best policy can be done through only these state action functions, which are these Q functions. So given a policy pi, if you're at state S and you take an action A for that, then the expected return for this state action pair, the expected return can be written in this form, which is what is the future return that you are expecting. This is the expected value in statistics form. If you're currently if at time t you are sitting at S, and at that time when you were sitting at S, you have taken action A, then what is the expected return? So with this state and this action, this expected return is actually the value of state action pair function under a particular policy. And the goal to find the optimal policy, we first have to find out the optimal state action pair function, which is basically the maximum over all the policies. So the whole goal, actually the actual goal, is to find out the best policy. But that policy basically relies on finding out the optimal state action function. And to find out the optimal state and action function, we have to rely on expected rewards. So that's a measure, expected return. Expected return is a measure to basically decide or compute the optimal state action function, which in turn gives the optimal policy for any reinforcement learning problem. So further, you can see here with a really, if you see this, the value of gt, that is this. If I replace this gt with its value, the state action function appears to be this. Given st and at, we can further simplify this notation by just writing that the state action function value at time t, when you were at state st and you have taken action at, is simply the expected return, which can be written in this particular form. So this here we replace this future returns as a recursively as a state action function, which is easy to show that this is doable. What is more important is that once you know the state action pair value as expected in terms of expected returns, now let's move to temporal difference. The temporal difference idea is the following: you have to estimate the best value of this Q. I'm replacing this capital Q just to refer to a big matrix, Q matrix, that actually holds all the state action function values. If you want to estimate this thing, if you want to estimate the state action pair value for state ST and you take an action AT, then by formula that is basically equal to this. The expected value of RT immediate reward and the Q value on the next state, and you take whatever action according to some given policy at the next state. So at ST plus 1 you have taken this action according to some fixed policy, some given policy. So if I add to this factor and subtract this factor, the formula doesn't change. But here is how the temporal difference update works. What happens basically is, this is what your target is. That is what you want to estimate. And this is where your current estimate relies. So the iterative update, let me call that K plus 1, the iterative update relies on the current value of Q. Then this is the target at the current value. And then you say, if this is my target I want to reach, and here at this position if I'm standing, then this subtraction is giving a gap between the target and where am I standing. So what if I move alpha steps to correct, to rectify, or to decrease this particular gap? So I'm sitting here, I'm off by this factor, so let's compensate that factor by this term alpha, and this is called the temporal difference update. And this is particularly an iterative method. And in this temporal difference update, there are two main algorithms. One is called SARSA, given a particular policy, and other is called Q-learning without any specific policy, and the update follows in the following way. First of all, see, we do not have the expected value. We do not have the true value, so we use these values as the estimate of this expectation, and by law of large numbers, if you do a lot of runs, these values, they actually converge to true expectation. So we remove this expectation and use this as an estimate of the expectation. So one simplification is that. Further, if there is a policy, then at state S plus 1, we have to sample a particular action with respect to that policy, and then we do our temporal update. In Q-learning, however, we do not rely on a particular policy to sample the action when we move to ST plus 1. Rather, we pick the action with respect to the greedy choice, which means if you're at state ST plus 1, there are several actions that are going on. We will pick the one that gives the maximum Q value. And it turns out in this Q-learning paradigm, the optimal state action pair is approximated directly without intervening with any policy. However, one thing must be noticed, that in the very beginning, to sample this particular action out of all, we may have either a random policy or maybe an epsilon greedy policy or maybe a decaying greedy policy and stuff like so. So the both SARSA and Q-learning, they are temporal difference learning algorithms. The difference between SARSA and Q is that in Q-learning, when you have taken an action and you reach to next state, the best action at the next state is estimated to be the greedy with respect to greedy choice, argmax. However, in SARSA, at the next state, there is a policy that guides what action to pick in the next state as well. So yeah, so that's SARSA and Q-learning. In the next video, I'm going to actually write this SARSA and Q-learning in algorithmic form. I will give you a step-by-step explanation how SARSA and Q-learning can be implemented. And in the video after the next video, we will be actually implementing Q-learning on our map rover example that we have seen in the earlier parts of this video series. So hope to see you in the next video, in the next part of this video series.